Hello everyone. My name is Dr. Deepak Yadav, and today we will going to discuss fringe transmission formula. This is one of the complex topic of antenna and wave propagation course that is taught in the EC third year. So, as we already discussed many things related with the antenna and wave propagation in our previous lectures, and this is one of the important formula which provide the information of how much power is required at the transmitter side to make a proper communication. That is how much power is required to received at the receiver side, that is represented generally by PR, and relation between PR and the transmitted power. So, to study these things, we have to discuss these topics today in this lectures, that is the radio communication links, field from oscillating dipole, that is how the dipole is radiating the electromagnetic wave, signal to noise ratio, fringe transmission formula, and antenna temperature and antenna impedance. Then the first thing is antenna aperture. How the antenna aperture affect the transmission of power and reception of power for a given communication links. So, as we all know that the pointing vector is nothing but the power density that is transmitted by the transmitting antenna, that is the total power over the complete sphere over which that power is transmitting. So, the power density or pointing vector is generally represented by a value S, or that is equal to S, and the amount of the power received at the receiving antenna is nothing but the power density received at the receiving antenna multiplied by the aperture area of the receiving antenna, AP. So, this is the effective aperture area that is going to be received the actual amount of power. So, the power that is received at a particular antenna in watt is equal to E square by eta, where E is the effective value of the electric field divided by eta is the impedance of the free space or impedance of the medium over which the transmission is carrying out, and AP is the AP is the antenna aperture, and it is also represented by S, that is pointing vector. So, it is also represented as S into AP. So, the power received is equal to S multiplied by AP. Now, we will discuss what is this AP, effective aperture of the transmitting antenna. So, let us consider this is the transmitting or receiving antenna, that is a horn antenna having the aperture area AP, and the electric field is superimposed over this over this horn antenna as it is vertical in nature. So, the side wall is behave as a conductor that short circuit the electric field vector which is very at the edges of the incoming electromagnetic wave. So, the effective area is actually shrink to a point which is only receive this much amount of electromagnetic vectors that is converted actually into the power. So, the total efficiency of the transmitting or receiving antenna is given by the effective aperture of the antenna divided by actual aperture of the antenna. So, this is known as the aperture efficiency, which is in this case if we consider this, let's suppose if the effective aperture area, so the total aperture area is AP, so the effective aperture area is AE. This AE is smaller than AP because the electric field that is received in the side edges must be short circuit, and the effective power that is received which is lesser than the received by the actual aperture. So, let us consider again a new scenario that in antenna that is transmitting having the effective aperture A, that is transmitting electromagnetic wave having electric field strength at that point of transmission is EA, and at a distance R from the transmitting antenna is ER, and let us suppose this antenna is radiating in a beam which is having the beam angle, that is ohm into A. So, the power radiated by the transmitting antenna, this is equal to P EA square by eta naught into AE, and the power received at this point which is having the electric field ER, P is equal to ER square by eta naught into R square into beam area of the received signal. So, these two power are equal. So, we can equalize this power, that is equate the equation number 3 and 4, and we find that the relation the relation that is already exist, ER must be related to EA, effective electric field that is radiated is equal to EA AE by R lambda. When we put this value of ER into the previous value over here and equate this equation, we find that lambda square is equal to AE into beam area. So this is the aperture beam area relation, in which the beam effective aperture of the antenna and the beam area that is radiated by the same antenna is related by a wavelength over which it is operating by this formula, lambda square is equal to AE into ohm into A. Now from this formula we can also derive the directivity. Directivity is nothing but 4 pi AE by lambda square. So if we put this value AE, that is lambda square by ohm A, we find that D is equal to 4 pi divided by beam area, and which is the actual this is the actual, that is the definition of the directivity, that is the field radiated over the complete 4 pi angle divided by beam area over which the field is actually radiated. So if it is radiated over the complete 4 pi angle, that is the angle of the sphere, and your beam is directed in this direction having the beam area ohm A, so the directivity is nothing but 4 pi over the complete area divided by ohm into A. So this is the directivity definition as well, and we can also derive the directivity by this relation. Using these two relation, we can get the directivity as well. Directivity can also be defined with the help of the maximum power received divided by average power, which is nothing but the same thing, the average power over the complete sphere divided by the maximum power over this beam area divided by average power over the complete sphere, and this is again a dimensionless quantity because it is the ratio of the power as well. So the directivity pattern is the maximum power divided by average power, and the relation with the directivity with the effective aperture of the antenna, D is equal to 4 pi A by lambda square, as we can see over here. Now, when the antenna is receiving, if the load resistance, that is antenna internal resistance, is equivalent to the radiation resistance of the transmitting antenna or the receiving antenna, then RL is matches to the RR radiation resistance, and in this case the maximum power is transmitted because both the impedance level is matched. So in this case the maximum power is transmitted from the load to the transmitting antenna. Now the another thing is the effective height of the antenna. So effective height of the antenna is again related with the amount of the electric field it is going to be received. So the total voltage that is generated by the antenna is equal to H time height of the antenna multiplied by the electric field received by the antenna. So the effective height of the antenna is the ratio of the voltage developed across the terminal of the antenna divided by electric field received by the antenna. So now if we consider an antenna that is lying in this arrangement, and this is a dipole antenna, and when the electric field vector is considered a little tilt, so the amount of the actual electric field received by this single polarized antenna, that is linearly polarized antenna, which is the intersection point of this vector, which is maybe a very small amount compared to the total height of the vector. So the voltage developed is again proportional to the amount of the field received, amount of the actual vector intersect with the length of the dipole. So the total field received is again depend on the angle of the polarization over which the wave is going to be incident over the linear polarized antenna. In case of parabolical antenna, in which all polarization can be easily received, it is it is free from the orientation of the electric field vector. So most of amount of the radiation is converted into the power in this case. So there is no problem with the orientation of the incoming electric field. So the effective height of this antenna may be differ with the effective height of this antenna, because due to the polarization the effective height going to be reduced, because the voltage developed is less in compared to the voltage developed over this this antenna. So the effective height is nothing but voltage developed divided by electric field. And if we calculate the relation between the effective height of the antenna and the effective aperture of the receiving antenna, that is effective height over here and effective aperture over here, from these two antennas, we can find the relation. If the load resistance is matched with the radiation resistance of the antenna, the maximum power is transmitted, and which is given by V square upon 4 RL. The maximum power transfer formula, P is equal to V square upon 4 RL. So in case the V is the voltage developed across the antenna terminal, which is nothing but H square into E square divided by 4 into radiation resistance. Now the power received is given by pointing vector into effective area of the receiving antenna. So this is nothing but it is E square A by Z naught. Z naught is the impedance of the free space. So if we equate this power, because this is the power that is transferred from the space to the antenna, and this is the power that is received from the space, and these two power are same. So if we equate, we find that H, effective height of the antenna, is equal to 2 times of under root of radiation resistance into effective aperture divided by Z naught, or we can find the AE, that is equal to H square Z naught upon 4 RL. So it is a clear relation between the effective aperture and effective height of the antenna, and which is because Z naught is constant for a particular antenna, radiation resistance be constant, and R is also constant, then effective aperture of the antenna is proportional to height square. That is, if a single dimensional antenna, it is equal to height only, but for a square it is height multiplied by height. The effective area of the antenna is equal to multiplication of effective height of the antennas. So these are the relation, that is the effective height and effective area of the antenna. Now the effective height or effective area of the antenna is also depend upon the type of the current that is flowing from the antenna. Like if we consider a lambda by 2 antenna over here, and the current distribution is not linear. Like for the linear current distribution, the current distribution is like this, it is constant at all the point over the complete length, while in this case the current distribution is sinusoidal. It is minimum at the edges and maximum in the center. In this case it is triangular. So if this kind of current distribution is here, the effective height is going to be reduced. Like for this case, for sinusoidal distribution, the average current value is 2 divided by pi, that is 0.64. So the effective height is effective height of this antenna is 0.64 times of the actual height of the antenna, that is 0.64 multiplied by lambda by 2. In this case, it is only 0.5 of the actual height of the antenna. So the effective height is actually half in case of when the current distribution is triangular distribution. So even if the current distribution also affect the effective height of the antenna, and for the different current distribution the value is changes. For the linear or constant current distribution, it is equivalent to the height of the actual antenna. Now, if we find the relationship how the current distribution can affect, we can calculate the current effective height of the antenna by this formula, 1 upon into I naught integration of from 0 to height of the actual height of the antenna Iz, that is current distribution profile over here, into dz. So this is equal to I average upon I naught into HP. Then if your I average is 0.64 of I naught divided by I naught, this I naught cancel, then we have the effective height, that is 0.64 over here. Now the fringe transmission formula. The fringe transmission formula suggests that the amount of the power that is transmitting from the transmitting antenna and it is received from the receiving antenna. If the gap between the antenna is R, then how much power is received at the receiving antenna when the particular amount of power, let's suppose PT, is transmitted from the transmitting antenna. Then the calculation of power that is transmitted or received by the transmitting and receiving antenna at a distance R from each other. Now, if we calculate the pointing vector at this point where the transmitting antenna is going to transmit it, let the power be PT, and let's suppose this antenna is not directional, it is just a point source in the space and which is radiated all its power in the complete sphere. It is not only the circuit. If we consider a 3D space and there is a point in the 3D space, it is radiating over the complete sphere. So the total angle, area of the sphere, that is 4 pi, if the distance is r, this is the receiving point, if the distance is r, so the total area, surface area of the sphere over which this PT power is transmitted, that is 4 pi r square. So the pointing vector that is received at this point due to the point source only, that is equal to S received is equal to PT upon 4 pi r square, where r is the distance from the transmitting over which to the receiving antenna over the point where we are actually going to find out the power, how much power is going to be received. So SR is equal to PT upon 4 pi r square watt. And if we consider this point source to a antenna which is having a gain in a particular direction, and this gain is represented by GT. Now this power, this pointing vector is now in a particular direction due to this directional antenna, and the total power that is radiating over the complete sphere is now directed towards the transmitting antenna with the gain of GT. So the power received or the pointing vector by the directional antenna is equal to GT PT upon 4 pi r square. So now we can write this pointing vector is equal to PT GT upon 4 pi r square. Now this power is actually transmitted toward the receiving antenna, but the amount of the power that is actually going to be received by the this receiving antenna is depend upon the effective aperture area of the receiving antenna. So this pointing vector is now multiplied by the effective aperture of the receiving antenna, that is the actual amount of power that is going to be received. So the actual amount of power received is equal to pointing vector that is coming multiplied by the effective area of the receiving antenna. So the pointing vector is PT GT upon 4 pi r square multiplied by the effective aperture of the receiving antenna. Effective aperture of the receiving antenna. Now the power PR is equal to PT GT AE upon 4 pi r square. Now we know the relation between the gain and the effective aperture of the transmitting antenna is nothing but GT is equal to 4 pi A by lambda square. So if we put the value of GT in terms of effective aperture of the transmitting antenna, we have the power ratio PR by PT is equal to AE, AER, AET upon R square lambda square. So this is the relation of the power that is received by the receiving antenna when a PT power is transmitting from the transmitting antenna in terms of the effective area of these two transmitting or receiving antenna and the distance between the antenna. Now we can also calculate this power ratio in terms of gain of the antenna and gain of the antenna and the operating wavelength, and this is nothing but if we put the value of AET by this formula. So AET is GT lambda square upon 4 pi and AER is equal to GR lambda square upon 5, and we adjust the value, then we get PR is nothing but PT GT GR upon 4 pi R by lambda whole square. So this is the fringe transmission equation in terms of gain of the transmitting and the receiving antenna, and this factor, this lower factor is known as the path losses, that is amount of the loss faced by the wave from the transmitter to the receiver, and that is nothing but 4 pi r square by lambda square. So this is the fringe transmission equation which is used to calculate the transmitting or receiving power from the different antennas. Now the field from oscillating dipole, and this is one of the topic which is a little involved the visualization of the how the electric field radiate from the oscillating dipole. So if we have the dipole antenna and if we provide a sinusoidal signal to the dipole antenna, the electron within the dipole is going to be vibrate, and this vibration of the electron start to radiate the electromagnetic field, as we will discuss in this topic. So if we consider a dipole of length L, and in the initially if your current is equal to 0, then due to this dipole there is some positive charge which is accumulated at the top and negative charge, and the electric field distribution is like the electric field coming out from the positive charge and dump into the negative charge with this arrow. Now if we apply the electric field, this positive charge going to move in this direction and negative charge is again going to move in this direction, but due to this the total amount of current is flowing in the downward direction, and the electric field distribution in the space is like this. It make a semicircular ring like structure over here, and at the time when the time period is equal to 1/4 times of the total time period, time is equal to, at this time these charges cross each other and this electric field lines are overlap each other over here, and which make a cut or superimpose over each other, and it going to be released into the space like this. It make a complete sphere, and it is going to be released in the space at point 3/8, and the now negative charge is going up and positive charge is going down, and the direction of this semicircle is going to be received over here. In the next, the situation is like positive charge is over below and negative charges over here at the time period t/2, and again due to the oscillating field, this negative charge is going down and positive charge going down, going up, which form a current which is flowing in the upward direction, and there is again a loop that is generated like this, which is having the value of electric field like this. So in this way the oscillating dipole can release the electromagnetic wave into the space, as we can see over here. This is the electric field dipole having having the oscillating current distribution over here, and due to this these kinds of loop is generated into the space. This is the electric field vector, this is represented by blue, and these are the magnetic field vector which is represented by a circular ring over here, and these two vectors are perpendicular to each other. If we simulate these things in the electromagnetic simulator, we can see electric dipole can radiate the electric field in this way into the space. The wave front is initially the wave front is spherical. It is in the 3D structure, in the 3D space. So initially the wave front is circular, but as the wave propagate into the space very deep, this wave front became flatter and flatter, and at the time of receiver it receive almost a flat wave front over here. And one more topic, that is signal to noise ratio. Signal to noise ratio is nothing but the signal power over the noise power for a particular transmitter or the receiver. This is the ratio of the signal power to the noise power, and it is represented by S and R. So the important thing is the noise figure. This is the amount of the signal to noise power that is entered in a particular device to the signal to noise power that is coming out from the particular device. So the noise figure of this device is represented by signal to noise ratio at the input divided by signal to noise ratio at the output. So thank you. So this is it for the today's lecture, in which we will discuss the effective height, effective area, signal to noise ratio, field from oscillating dipoles, and fringe transmission formula. Thank you.